Hello, my name is Ryan Cumings. My project is the laser communication relay. My advisor is Dr. Saleh Faruque. The tasks for this project can be broken into first semester and second semester tasks. The first semester tasks involve designing an optical receiver module. This module will utilize photodiodes in a differential configuration. The optical transmitter module. This module consists of a laser diode emitting light in the near infrared spectrum. Signal demodulation. This will include amplitude modulation. For this we'll utilize an envelope detector. Frequency modulation consists of a slope detector followed by an envelope detector. Amplitude shift keying, be an envelope detector followed by a Schmitt trigger. Frequency shift keying will be a slope detector followed by an envelope detector followed by a Schmitt trigger. And then phase shift keying, still under investigation. Signal coding and decoding will be a second semester task. For this, plan to use convolutional coding for binary data. This will be implemented in a programmable logic device. The power supply is intended to use a solar panel. For this, we'll have to utilize low power components and circuit design and manufacturing. The circuits should be laid out for high speed and fidelity. The system block diagram is shown on the right. The transmitter module will consist of the signal input, the modulation and coding, and the transmitter. The laser communication relay will have functions of receiving the signal, demodulating it, processing it, modulating it again, and then transmitting it again. And then finally, the end user will receive the signal, they'll demodulate it, and then have access to the original signal input. 50 ohm interconnections are going to be utilized for all signals going to and from the transmitter and receiver in the processing stages. The processing section will utilize signal regeneration for frequency modulation, amplitude shift keying, frequency shift keying, and phase shift keying. An automatic gain control circuit will be required to regenerate amplitude modulated signals. High power, high speed devices are currently being utilized during the prototyping phase. The purpose of using these devices is to allow exploration of the capabilities of the system without running into device performance issues. Low power devices will be utilized later in the design process. The receiver module is designed to be a differential photodetector. It utilizes photodiodes to provide a current signal. One photodetector cancels out the ambient light. Due to lack of ambient light at 850 nanometers, this provides a very high fidelity signal, as will be shown later on. The photodiodes have a good sensitivity due to the low impedance bias provided by Zener diodes. 5.6 volts was chosen due to the low temperature coefficient to guarantee consistent performance during testing. The transimpedance amplifier will amplify the differential current. The proposed automatic gain circuit will be utilized at a future point to send consistent input signals to the processing module despite the large dynamic range of the laser signal. The model of the photodiodes is shown on the left. This model was developed based off of the 5.6 volt bias from the datasheet. On the right is the low impedance bias. A constant current source and sink feed the Zener diodes to create a constant voltage. The current draw from the diodes through the bias is negligible compared to the current through the Zeners. The Zener diodes have a low dynamic impedance as well, resulting in a low impedance return past the ground. The transmitter module must accurately recreate the command signal. The 850 nanometer laser diode provides the signaling to the receiver. Again, infrared was chosen due to the low ambient levels. Rapid rise time is also desirable to ensure that signal distortions due to rise time are not of concern. This module was the first to be soldered to a perf board. On the breadboard, alligator clips and leads were required to position the laser diode to be in line of sight of the receiver. This resulted in a 9 nanosecond lag for the current signal. This, coupled with the capacitive load of the laser diode, resulted in oscillations which showed up as noise on the receiver. When the laser diode was placed on the breadboard, the ringing was excessive due to the high capacitance of the breadboard. As a result, prototyping was required to be moved to a perf board. The high-speed op-amp unfortunately does not have the required voltage range to drive the laser diode directly and sense the current as well. This forced a requirement to utilize a transistor to drive the laser diode. A BJT was chosen specifically because it is a current-controlled current device. MOSFETs have additional capacitance which reduces the speed and rises ringing. A current command is desired because of the linear relationship of current to optical power. A 300 MHz op-amp is currently being utilized to force compliance of the laser diode to the command signal. To compensate for the ringing due to the capacitive load of the laser diode, a phase lead compensator was utilized. First, the period of the oscillations was measured when a step input is commanded. The frequency of the maximum phase compensation was then selected to match the frequency of the oscillations. This resulted in a crisp and clean edge with minimal overshoot when a step input is commanded. This is a picture of aligning the laser diode with a photodiode. Red lines are added to give perspective of the path of the infrared light. The photodiode on the right results in a positive output from the receiver. The photodiode on the left results in a negative output from the receiver. To align the laser diodes, an infrared sensitive material shown in the picture will illuminate when the laser falls on it. A shallow angle results in optimal coupling. The small distance ensures consistent operation when applying different signals. The picture on the left is a 1 kHz square wave. The one on the right is a 1 kHz sine wave. The yellow trace is the current output from the laser diode. Note the sharp edge on the square wave. The blue trace is the selected output from the receiver. In this case, this is the result is the direct output from the receiver. For AM demodulation, a simple envelope detector is currently being utilized. A diode ring mixer would be considered a performance enhancement. Right now, the circuit only rectifies the positive peaks of the signal. The output will be taken after the DC blocking capacitor C2. This circuit can detect both the negative and positive going photodiode. The AM carrier signal is set to 1 MHz. This results in a clean demodulated signal. Notice the distortion on the negative half cycle of the output sine wave. The envelope detector also results in distortion of the square wave due to the DC blocking capacitor. The pulse width modulated signal has proved to be an effective method of transmitting signal. By sending the PWM signal to the same envelope detector as the AM signal, we were able to recover the original signal. The pulse train frequency is set to 5 MHz with a duty cycle of 50%. The deviation is set to 25%, which resulted in the cleanest sounding signal. As you can see, there is much distortion on both signals. In closing, the transmitter module is working well enough to continue moving forward with the prototyping the remainder of the signal path. The receiver module is working well, but changes in the future might degrade performance, such as switching to a visible light laser or selecting a photodiode with a larger aperture. So far, signal demodulation seems to be right on track with standard circuits utilized for demodulation. In the future, work is going to be on modulating arbitrary signals. Listening for the 1 kHz tone is not as pleasant as it would seem. Additional work would include passing a signal through the relay and then construction of a relay. Once the relay is complete, we'll focus on processing the signal and then regenerating it. Thank you for your time.